chapter 7, the structure of atoms and periodic trends. So here's the chapter outline. So the first thing we're going to talk about is the Pauli exclusion principle, probably the biggest driving force in electron orientation or orbital filling. Atomic subshell energies and electron assignments, electron configuration of atoms, electron configuration of ions, atomic properties and periodic trends in chemical properties. So the arrangement of electrons in atoms. So we go through our quantum numbers again. So all of this can be related. Maybe you encountered this before. I don't know, with electron filling, you know, like you fill from the lowest energy to the highest energy. It's the Aufbau principle. I don't know exactly what background each one of you had, but all of that, at least if you learned that before, is driven by these quantum numbers that we've just learned about, which is less likely to have been encountered. But anyway, so the shells are like, for example, n is equal to 1 or n is equal to 2. Usually whenever we're talking about this, we're always giving the example of the hydrogen atom, but other atoms also have the same sort of arrangement. So L can be any value from 0 up to n minus 1. Then the orbitals are going to be ML, where it goes from minus L through 0 to plus L. All right. So yeah, so like for example, the p orbital in the n is equal to 3 subshell. It's going to be n is equal to 3, L is equal to 1, ML has values from minus 1, 0, plus 1, which is going to be from, what do you call this? From minus L to plus L, and then MS values for any one of those is going to be plus or minus. Okay, for each one of our orbitals. So the Pauli exclusion principle, this is a huge driving factor in these orbital configurations. So the Pauli exclusion principle is sort of a statement from this scientist, Wolfgang Pauli, that no more than 2 electrons can occupy the same orbital. And if there are 2 electrons in the same orbital, they must have opposite spins. That's MS. So they can have the same N, they can have the same L, and they can have the same ML values. However, the last quantum number, the MS, must be different. And that's because they must have different spins. Otherwise, we end up with an incorrect orbital assignment. So this leads to the general statement that no 2 electrons in an atom can have the same set of 4 quantum numbers. So there's 4 quantum numbers. There's N, there's L, there's ML, and there's MS. All of them can be the same, NL and ML, except for MS. MS is always different. So quantum numbers, electrons in an atom are arranged by quantum numbers. So the principal energy levels are the shells, that's N. It goes from, n is equal to 1, the ground state, all the way up to N is equal to infinity. Angular energy levels then, so these are the subshells. So this is L. Oriented energy levels, that's ML. Well, N is equal to 1 is the ground state in hydrogen atom. Whatever the valence electrons are in is the ground state for other atoms. So within an individual orbital, there may only be 2 electrons differentiated by their spin. So spin states is sort of the electron has the value MS. So 2 general rules that help predict electron assignments. Electrons are assigned to subshells in order of increasing N plus L value. So remember, N is the principal quantum number, and L is the subshell. So N, for example, is equal to 2, and L is equal to values of 0 or 1. So that means n plus L for any of the orbitals in the n is equal to 2 levels, so that can be either 2 or 3. And so what this means is that we would fill this before we would fill this. Because we fill it in order of increasing n plus L value. For two subshells with the same value of n plus L, electrons are assigned first to the subshell of lower n. So if this can happen in examples, for example, say we have the n is equal to 3, L is equal to 0 level, that also has n plus L is equal to 3, because 3 plus 0 is 3. And if we have the n is equal to 2 level, where L is equal to 1, so that's the p orbital, then n plus L is also equal to 3. So how do we then differentiate between those? 2 plus 1 is 3. Like, how do we decide which one of these gets filled first? Well, the answer is the one with lower value of n. So it would be this one goes first. And then this one second. Okay. So in the hydrogen atom, all of the orbitals of a subshell are equal in energy, so they're degenerate. So here we have, like, they're degenerate, meaning that they're on the same. Okay, that should be a straight line. Anyway, so they're on this straight line here, and they have the same energy for the 2s, the 2p, the 3s, 3p, and 3d. They all have the same energy as well. They are what is called degenerate or equal in energy. But whenever we start adding more electrons, we have multi-electron atoms, the energy levels are non-degenerate, and we can see this here. So for example, the 2s and the 2p are separated by this energy difference here. And then the 3s, 3p, 3d, or 4s, 3d, you can see that the energy level of the 4s is actually lower than the 3d. This is a multi-electron atom. Things start to change because of the effects of multiple electrons interacting with each other. So that's why this is one of the reasons why also the Bohr model that we discussed previously doesn't work so well once you start to increase the number of electrons, because it can't really account for this idea of electron interaction with each other. But of course, we have new theories that are better at doing that. But they're all kind of based on that model. So it was very useful. And then we see here this idea of how we can sort of, what's the word I'm looking for? How we can sort of understand this change in energy level, and why the 4s, where n is equal to 4, is going to be lower in energy than the 3d, where n is equal to 3. And it's because of this idea of this n plus L giving us sort of the energy of the orbital and giving us the orbital filling. So we can see a calculation for it here, where the 3d and 4s orbitals have had their n plus L's calculated. So n plus L for the 3d orbital is 5, whereas n plus L for the 4s orbital is 4. And so you can see that here. And so the 3D then, if n plus L is equal to kind of the energy, or is a sort of a proxy for the energy, then we can see that the 3D is higher in energy, and so the 4s is going to be lower in energy. So the 4s gets filled before the 3D, at least in multi-electron atoms. Things can get a bit different whenever we start putting these into molecules and what have you, but for now, we're considering only atoms on their own in the gas phase. And so what ends up happening is that the 4s gets filled before the 3D. And we can also kind of see that in our periodic table when we go to that later on. So here again is the same thing. They've drawn out the energy levels, the orbitals. in increasing energy. There's the 1s, the 2s, 2p, 3s, 3p, 3d. And then they have done over here the calculations. They've got the n values, they've got the l values, and they've got the n plus l values. And then they're showing how we can sometimes have systems which have the same sum, but we fill based on the lower n value. And so here it is again, just to reiterate this point, this is the subshell filling order. So we have the 1s here that's filled before the 2s where n plus l is 2. And then we go through to the n plus l is equal to 3 series. And so that's 2p gets filled before 3s. That's because 2p has a lower n value, whereas the principal quantum number for 3s is 3. So it gets filled after 2p because 2p has a principal quantum number of 2. Then we go around here. So n plus l is equal to 4 in that series. So there's 2 that fulfill that. There's the 3p, there's the 4s, and then this gets filled to here. 3p before 3p because it has the lower principal quantum number. Then n is equal to 4, the 4s because it has a higher principal quantum number, and so on. You can just go through that until we get to like the 8s orbitals. Things like we generally sort of only get to about here or here in most of our systems. We never really get to the very, very high systems, at least for atoms and what have you. I mean, in practicality, I mean, things like this do exist, of course. These higher quantum numbers do exist, but generally, whenever we're dealing with it, it's n is equal to 5 and below that we'll be dealing with. N is equal to 4 actually is probably the highest, 3D, 4s, that type of thing. The first row of the transition metals. So effective nuclear charge then. So this is the, so we have a nucleus, right, with all of the protons in it. Then we have the electrons, which exist in different principal quantum numbers around the nucleus. And we talked about the idea that as n gets larger, g of that orbital also gets higher. And so that is because it's held less strongly. So the inner electrons, so the n is equal to 1, n is equal to 2 levels, those are closest to the nucleus for all of the positive charges. And so those feel the strongest attraction. Then as we start to move further and further away, we get to the electrons on the outer or the valence shells. And those do not feel this attractive force as much because there are electrons of lower principal quantum number which get in the way, and those sort of block or shield the nucleus from the outer electrons. And so we can actually calculate this effective nuclear charge pretty well. Calculations can be done using Slater's rules, or we can do it here just very simply by counting electrons. And so effective nuclear charge is the Z star, the Z asterisk. So the Z here is the same sort of as the atomic number that we had, so the number of protons. So the Z star is the net charge experienced by a particular electron in a multi-electron atom, resulting from a balance of the attractive force of the nucleus, because the nucleus is positive, and the repulsive forces of other electrons. So the electrons are generally all negatively charged, and so they will generally sort of repel each other, like negative charges repel each other. So the effective nuclear charge then increases across a period because owing to incomplete screening by inner electrons. And so this explains why E in the 4s electron is, the energy of the 4s electron is less than the energy of the 3p electron. So the effective nuclear charge is approximately equal to Z, which is our atomic number, minus the number of inner electrons. So we can calculate for that. So the charge felt by the 2s electron in lithium is going to be the effective nuclear charge is equal to 3, which is the number of protons in the nucleus, minus 2, which is the number of inner shell electrons. So that's the 1s electrons in this case, because you remember it goes 1s, and then the next one would be n is equal to 2, l is equal to 0, which is the 2s orbital. So these are from the 1s orbital. Remember, we're talking about the 2s orbital, so there's only the only electrons closer to the nucleus will be the 1s. So that's why all of these values here are 2. But the number of protons in the nucleus changes. So, for example, lithium has 3, beryllium has 4, and boron has 5. And so that means that these 2s electrons are held more strongly as we increase Z. So as Z increases, so going across the period, going across, Z increases. What we see is that these 2s electrons are held much, much tighter. So the 2s electron in lithium is quite easy to, it's not really held that strongly, at least compared to boron. So we can see here that the how the effective nuclear charge and the distance is related. So as we increase the N number, so for example, this sort of lighter red that you can kind of see here, that's going to be the 1s electrons, the probability of finding the 1s electrons. This dotted line here indicates the region of highest probability for 1s electrons, and we can see that they are held much closer than the 2s electrons, where they are predominantly found outside of the region that the 1s electrons are found within. And so this is the probability distribution for 2s electrons, and it's a function of this effective nuclear charge. So these electrons are found further away because they're not held as tightly. So Z star is the nuclear charge experienced by the outermost electrons. You can see this dashed line has been continued to here, which is sort of like the electron cloud for 1s electrons. So each one of these dots is kind of like a predicted location for the electron around the nucleus, which is here at the center of this cross. So there's the nucleus here, which is filled with protons and neutrons, and then the electrons are around here. And so you can see that after we go past this line, there are some electrons. I mean, some can still exist, like there's this tiny little bit here, but it's very, very low probability. Okay, so here is the orbital, not the orbital, the periodic table that I was talking about earlier. So we have a bunch of, we have the different blocks. We have the S block, here on the left-hand side, S block. We have the P block here, and we have the D block, and we have the F block. We won't really consider the F block at all. In fact, we probably won't even get past the 4th period of the periodic table, which is here. So usually whenever we're filling in the electrons, what we do is like, we start at the top left, so 1s here. That's hydrogen and helium. I know it's not written here, but just bear with me. Hydrogen is here, helium is here. So we go 1s1, 1s2, and then the next ones is going from 2s, 2s1, 2s2. So we fill from left to right. Then we have the 2p orbitals. So there are 2p electrons. So that's 2p1, 2p2, 2p3, 4, 5, 6, and 3s, 3p, again, the same, then 4s, and then 3d. So you can see now as well that even the periodic table also has this idea of a multi-electron atom having the 4s orbitals filled before the 3d orbitals, because they come before the 3d orbitals in the periodic table. And so what we're doing is we're filling from the bottom up. We're following the Aufbau principle, which you may have encountered before as well. So the Aufbau principle starts with the 1s, then goes to the 2s. So the Aufbau principle, we go from lowest to highest quantum number, or principal quantum number. So using the periodic table for the electron configurations, it's easier than memorizing the filling order. So for example, say we have, so this is boron here, this one here. So to fill up the boron, we've got 1s1, 1s2, 2s1, 2s2, 2p1 gets to here. So that's how we would do it. You can do that for any. So like this is hydrogen, so it's 1s1, you're done. Helium, 1s1, 1s2, you're done. So you can do that for any atom, and that means you don't need to actually necessarily memorize the filling order. You can just use the periodic table. So can we figure out the order of filling of orbitals? So one, we could memorize that it's filled 1s, 2s, 2p, 3s, 3p, 4s, 3d. You could memorize that, sure. But a better way would be to try and use the periodic table. So this is much easier. So in almost all, except for quiz number 1, almost all quizzes and what do you call this, and exams and stuff, you will have access to a periodic table. And so you can use that if ever you need to, what do you call this? If you need to determine the filling of the orbitals. So electron configurations, the way in which electrons are arranged around the nuclei of atoms. So we have orbital filling. So we follow Aufbau principle and Hund's rule. So what happens here is the Aufbau principle is the lower energy orbitals get filled first. So that's like the 1s. So basically that's, in other words, it's saying that we fill from n is equal to 1 to n is equal to 2, and then on until we get to n is equal to infinity. Then we have Hund's rule, where degenerate orbitals, those of the same energy, are filled with electrons until all are half filled before pairing of electrons can occur. So this only really applies whenever we start to get to p orbitals. So because those are degenerate. So in the case of n is equal to 2, L is equal to 0, or L is equal to 1, sorry, those are our p orbitals. So that's our 2p orbitals. We have 3 of those because remember ML, the number of orbitals is equal to 2L plus 1. 2L plus 1 for L is equal to 1 is 3. So we end up with 3 orbitals. 1, 2, 3. Common way is just to draw them out like as a line, like this. So say we were filling these, we would fill it as this. So it would be 1, 2, 3, 4, 5, 6, and so then we have filled in our p orbitals. What we wouldn't do is, for example, say we had 2 electrons, we wouldn't put both of them into the same orbital at once. We must always half fill the degenerate orbitals before we fully fill them. So it says here, degenerate orbitals, those of the same energy, are filled with electrons until all are half filled before pairing up of electrons can occur. The Pauli exclusion principle then, so this is individual orbitals only hold 2 electrons and each should have a different spin. So s orbitals can hold 2 electrons, p orbitals can hold up to 6 electrons, d orbitals can hold up to 10 electrons, and f orbitals can hold up to 14 electrons. So the Hund's rule then in action, I suppose. So degenerate orbitals are filled with electrons until all are half filled before pairing up of electrons can occur. So consider a set of 2p orbitals here. So we fill it up in this manner. So they've drawn full arrows because that's easier to obtain in a computer setting. So yeah, both are perfectly fine. Like you can have arrows going up like this. You can have half arrows. You can have them through the line. You can have them above the line. It's all good. I just was originally taught to do it like this, so that's the way I still do it. So long as people understand what you are trying to convey, it doesn't really matter. So degenerate orbitals are filled with electrons until all are half filled before pairing up of electrons can occur. So here we have 2p, we have 2p orbitals. So we have the -1, we have the 0, and we have the +1. So those are our ML values. Right now we have half filled. So we have what is called a 2p3. This is this superscript here. That is indicating that we have 1, 2, 3 electrons. Usually we know that there is 1 in each orbital because of following of Hund's rule. So we always follow Hund's rule. So we know that each orbital of the 2p will be half filled. That is our assumption based on Hund's rule. Then after that, we would start to fill the orbitals like this. So you half fill them first, and then you fully fill them. The Pauli exclusion principle then, so individual orbitals can only hold 2 electrons, and each should have opposite spin. Remember that we also have this idea that one should point up and one should point down. They should have 4. The quantum numbers that they have should all be different. So we consider a set of 2p orbitals. So we have 2p orbitals here. This is 2p6 now, because there are 6 electrons. We have 1 electron, 2 electron, 3, 4, 5, 6. A half are spin up, half are spin down. And so the convention is to write up, then down. So yeah, so usually, like I think I mentioned this earlier. So we have the p orbitals. So we would fill them up, half filled, pointing up, and then point down. It's really just convention. They're effectively the same thing, but the convention is to write up, then down. So you would generally be expected to write it in that order as well. Okay, so the last thing, all right, I'll talk about this. Yeah, I'll talk about it. So another way of looking at electron configuration is the orbital box notation. So this is where we draw out the orbitals as boxes, basically. You know, it's pretty self-explanatory. To represent our different orbitals. So electrons fill the orbitals from lowest to highest energy. That's the Aufbau principle. So the electron configuration of an atom is the total sum of the electrons from lowest to highest shell. So nitrogen has an atomic number of 7, therefore it has 7 electrons. These are arranged into the orbitals until we have filled them. So we start from the bottom and then we work towards the top. So the first one to be filled is the 1s orbital. So we could also find out the quantum number here. So if I'll put n at the top, and then I'll put L, and then I'll put ML if it exists. So n is equal to 1 here because it's the s or 1. So then we have 0, and then we have ML value of 0. So we have the 1s orbital. Okay. Then we have n is equal to 2 for both the 2s and the 2p. We have L is equal to 0. We have L is equal to 1, and here we have ML is equal to 0, and we have here we have -1, 0, +1. I mean, you could write it as +1, 0, -1 if you really wanted to, but convention is usually like minus to plus, but yeah, it's all good. So long as you realize that there are 3 orbitals. So we fill up from the Aufbau principle, we fill up from the lowest, which is 1s, then the 2s, then the 2p. We wouldn't fill, for example, 3s before 3p. That's not what we do, because 2p has a lower principal quantum number. Even if n plus L for 2p is equal to 3, n plus L for 3s is also equal to 3. So n plus L equal to 3, and is also equal to 3. Then we half fill each based on Hund's rule, pointing up just by convention. And so we end up with an electron configuration in SPDF notation as 1s2, the 2 here, because we have 2 electrons here in our orbital box, 2s2 because we have 2 electrons in our orbital box, and then 2p3 because we have 3 electrons in our 2p orbital boxes. So there's 1, there's 2, and there's 3. So we would know that these are half filled because of that Hund's rule. So we have 1s2, 2s2, 2p3 for nitrogen. And if we had a periodic table, we could also like do this sort of electron configuration pretty easily. All right, so that'll do us for today. We managed to get through that. Okay, so I hope my internet connection wasn't too bad. Still have some battery, so we're all good. So electron configurations, Aufbau principle, ground state, and this is sort of like a summary, I guess. Aufbau principle, ground state, electronic configuration. Electron goes into the orbital with the lowest available energy. No more than 2 electrons per orbital. Remember that ms can have values of +0.5 or -0.5. And the electron goes into an empty orbital if available, Hund's rule, and then we pair them up. So electron configurations, for example, hydrogen, helium. So this is 1s and or 1s1, 1s2. So it's 1. So both of these have the electrons in the 1s orbital. Hydrogen is 1s1 and helium is 1s2. Lithium to neon then, so this is where we fill up the N is equal to 2 level. So lithium has 1s2, 2s1, and then so on. Sodium, we have N is equal to 3. And potassium, N is equal to 4. So like the valence shell of potassium is going to be like 4s1, so that's the outermost one, and sodium is going to be 3s1. So more on electron configuration. So we use a numbering system to indicate electrons in an atom. So it is given first by a number 1, 2, 3, or 4, etc., dictated by the period number electron shell. So the first period is 1, second 2, 3, 4, as we go down the periodic table. This generally also corresponds to the principal quantum number of the valence electron, although not always. Then follows a lowercase letter N, S, P, D, F, indicated by the group from the periodic table orbital type. So remember, like the alkali earth and alkali earth metals, those are sort of S block elements. So usually if the electron is from there, it will go into the S block. And P is the main group and D is the transition metals. Then follows a superscript given over the letter, so indicates the number of electrons in that orbital. So for example, hydrogen is 1s1. So the 1 comes from the period, which is up here. S comes from the orbital type. And then the 1 comes from the number of electrons that are actually in that orbital. Lithium then, so it's commonly used in batteries, lithium ion batteries, like the laptop that I'm using right now, maybe your cell phone or mobile phone or tablet or devices that you have, generally run on rechargeable batteries, which are by and large mostly lithium ion batteries, very, very important. High energy density, they can be quite small, very, very instrumental in creating the convenience that we have today with our technology. So lithium is in group 1A. It has atomic number 3. It has 3 total electrons, and this is the electron configuration here, 1s2, 2s1. So we can see different ways of writing it out here. So we've got, like, for example, if this is energy here, E, I'll just write E for now, like so. Then we have 1s, 2s, and so on. Then moving on up, we have the box notation here, which has 1s and 2s orbitals. We also written out the 2p orbitals because they do exist on the in the lithium potential orbitals. 1s2, because this is the 1s orbital and there are 2 electrons, so 1s2, and then 2s1, so this is the 2s orbital, there's 1 electron, so 2s1. We get filled up like this, that's also okay. Write it out like this. There are multiple ways to do the same thing. Then for beryllium, we are pairing an electron instead of putting it into the 2p orbital, because the 2s orbital is lower in energy again. So this is the energy here, so it's E. So lower energy is the 1s, then the 2s, then the 2p, and then 3s, and then the 3p. This is in group 2a. The atomic number is 4, meaning we have 4 total electrons in the element. The configuration is going to be 1s2, 2s2. So this is the 1s orbital here. It has 2 electrons, that's 1s2. Then this one here is the 2s orbital box, and it has 2 electrons, so it's going to be 2s2. Boron then, which can be used as a polymer in certain ballistics protective gear. Boron is in group 3a. It has atomic number 5, meaning that it has 5 total electrons in its elemental form. The electronic configuration is going to be 1s2, 2s2, 2p1. So energy is here. fill it up from lowest to highest energy. So 1s1, then 2s2, then 2p1. So remember the 2p here, it represents all of these orbitals here. Carbon then, so this is in group 4. I mean, we're all pretty familiar with carbon. I guess the simplest form is pencil lead. I don't have a pencil here. Pencil lead, it is made of graphite, which is a form of carbon. Again, energy here. We fill up using the Aufbau principle from lowest to highest energies. So 1s1 or 1s2, 2s2, 2p2. And then from Hund's rule, we fill up empty orbitals before we fill up filled orbitals of the same degeneracy. So we have here the atomic number 6, which means we have 6 total electrons. So we fill it at lowest energy, 1s2, next lowest energy, 2s2, and then the next lowest energy is the 2p orbitals. We have 1, 2 in the 2p orbitals, so it's 2p2. It is from this notation here, where we write it out like with letters and numbers, this is implying this 2. It implies that we have them in different orbitals. So for example, based on this configuration, 1s2, 2s2, 2p2, I guess you could say that for the p orbitals anyway, there are 3 of them, right? So you could, I suppose, in theory, say that this is also 2p2, but that's not following Hund's rule. And so it must instead be this one here down at the bottom. Nitrogen then is a gas, it surrounds us. It's what, like 70, 80% of the atmosphere. It's an inert gas. It doesn't really react with anything. So 1s1 is the lowest energy. So we fill using the Aufbau principle from lowest to highest energies. How many electrons do we have? We have 7 total electrons because we're in group 5a. We have atomic number 7. This is our box notation configuration here. So we have 1s2 as usual, 2s2 as usual. So this is the inner sort of sphere. These are the inner sphere orbitals. Then we have 2p3. So this 3, again, following Hund's rule, means we have 1, 2, 3 orbitals half filled. We do not have a system where we have a pair and a single. And then an empty orbital here. That doesn't follow Hund's rule and is not allowed according to our rules and experimental observations. Oxygen then is in group 6a. It has atomic number 8. It has 8 total electrons. It has a configuration of 1s2, 2s2, 2p4. Energy is going up here. We have, again, following the Aufbau principle, we go from lowest to highest energies. This time, however, with 1s2, 2s2 as usual, we have 2p4 now. So in our 3 p orbitals, we have 4 electrons. So we have a pair and we have 2 singles. This is because going from the previous example, we had nitrogen, which is, we had 3 half-filled orbitals. Now we're allowed to pair them because there is no empty orbitals. So the next electron can be a pair. It'll be spin down, however, because remember with the Pauli exclusion principle, none of these electrons can have the same 4 quantum numbers. And so all of the p orbitals have n is equal to 2, or the 2p orbitals, n is equal to 2, l is equal to 1. And then ml is obviously equal from -1 to +1. So 0, +1. Okay. So we can then fill in the electrons like that. So if we, for example, this one here was -1, then we have ms values of plus and minus a half, plus a half and minus a half. All right. Fluorine then, so it's in group 7. Again, we're doing something similar. We have atomic number 9, 9 electrons, 1s2, 2s2 as usual. Energy here on the left-hand side means that we're going to fill using the Aufbau principle from lowest to highest energies. the 2p orbital is where most of the interesting things happen now. So since we have 5 electrons in the p orbitals, as shown here, 6 is the maximum we can have spread over 3 orbitals. So we're going to have 2 filled orbitals and 1 half-filled orbital. And then the last one here is neon. It's in group 8a. It has atomic number 10 with 10 total electrons. So it's got the configuration of 1s2, 2s2, 2p6. And so we fill in our electrons again according to high or lowest to highest energy, following the Aufbau principle. So Aufbau. Okay. And then following Hund's rule again, we have filled orbitals now. We have 6 electrons in 3 2p orbitals, which means that we're going to have everything paired up. And we end up with filled orbitals. So this is the end of period 2, the end of the second period. The second shell is full. And going on now, the next electron that we get, so i.e. the 11th electron, which is 11th element, which is sodium, is going to have electrons in the 3s orbital. It's going to be 3s1. We've filled up now with neon. We have reached the end of the second period. The second shell is full. The next one that we go to, we will be entering n is equal to 3 principal quantum number orbitals.